Hey, there we are. Hi, everybody. I'm Phil Lamar, and welcome to NASA's Ask the Astronomers Live, the show where you can ask live astronomers, no holograms, your questions as we chat about some of the most amazing things in our universe. For instance, today, we're going to be taking a deep dive into the deep end of the universe and find out how one single image of the sky can yield a 3D journey through 13 billion years of cosmic history. Now, for those of you joining us on Facebook or YouTube, you can go to the comment section to put in your questions. And that way we can give them and get answers from our astronomers. And also, everybody watching, please make sure to visit our website at universeunplugged.org, where you can find out about upcoming shows and also see lots of really fun astronomy videos. Now, our guests today are two astronomers who have been studying the farthest reaches of the universe. Let's say hello to Dr. Frank Summers from the Space Telescope Science Institute. Hi, Frank.
Hi, everybody. Hi. Good to see you, Phil. Nice to be here again.
Yeah, thank you for coming back. And Dr. Brian Siana from the University of California at Riverside. Hi, Brian.
Hey, everybody.
Now, can you guys please educate me? Our audience probably already knows. But tell us a bit about yourself and the work that you've been focusing on. Frank, why don't you start?
Okay. I'm an astronomer in the Office of Public Outreach at the Space Telescope Science Institute in Baltimore, Maryland. We're the scientific home of the Hubble Space Telescope, and we are the scientific home of the future James Webb Space Telescope, as well as the Nancy Grace Roman Space Telescope. I have done all sorts of public outreach for press releases and education and websites and planetariums and museums. And what I specialize in, as you'll see today, is visualizations of astronomy data. So I actually sort of call myself an astrophysicist for an astronomer who does visualizations.
Ah, cool. Now, is it coincidence that all of these telescopes are housed in Baltimore?
Well, they aren't housed in Baltimore. Of course, they'll be in space, right?
Right, yes.
But we have made it one of our missions as a company to try and bid on contracts to support the space telescopes. We're the Space Telescope Science Institute. So we like to be the science home of space telescopes. It's kind of in our name.
That's pretty on brand. Yeah. Brian, being the new guy on our chat today, we need to know what you're about.
Okay, thanks. Yeah, I'm a professor at the University of California, Riverside, and I study the very early universe and how galaxies and stars form in the very early universe. And I'm an observer, so I do that using telescopes, including the Hubble Space Telescope, but also really big telescopes that are on the ground. So the University of California runs one of the largest optical, visible light telescopes on the ground, the Keck telescopes in Hawaii. So I use those telescopes to study the really early universe and how stars form in the first galaxies. And I'm really interested in how the starlight from those, early galaxies escapes out of the galaxies and affects all of the gas that's in the volume between the galaxies. That's kind of my area of interest.
Oh, fascinating. And it's interesting because you're dealing with Earth-based telescopes as well as space telescopes. I'm trying to think now, in the olden days, before there were space telescopes, did astronomers have to go live on mountains to really do the job well?
They certainly had to spend a lot of time there, or drive back and forth on pretty dangerous, windy roads up mountains. Yeah, that's pretty common.
Right. And for you guys, if not for space telescopes, you'd have to live someplace with less light pollution. It's like, anyway, enough about the nitty gritty of your jobs. Let's get to our topic today. Now, today we're talking about the farthest galaxies in the universe, specifically those seen in a particular image it's called the Hubble Ultra Deep Field. That's the name of the image?
Yep.
That's right.
And that was, of course, taken by NASA's Hubble Space Telescope. Brian, can you talk to us about the Hubble Ultra Deep Field? What is deep field?
Right. So the goal with the deep field is to detect the faintest, most distant objects that we can possibly detect with our best telescopes, to kind of go as extreme as possible and seeing the faintest, most distant things. And in order to do that, we have to do a couple of things. We have to, and most importantly, we have to avoid anything that's in our way, that's nearby. So we don't want to point at anything that's in the solar system, planets and dust in our own solar system. So we avoid those things. The Milky Way, our own galaxy, is pretty bright. You can see it at night, right? That swath across the sky has lots of stars and gas and dust in it. All of that would obscure our view. So we avoid that entire swath entirely and look at a different direction. And then we have to avoid other bright stars and nearby galaxies. And once we find a good region between all of these bright things, and then we can finally see a dark region of the sky. Once we do that, we get our best telescopes. In this case, for taking images, there's nothing currently that beats the Hubble Space Telescope. And we point it to that perfect location in the sky where there's nothing in our way. And then the next thing is to detect things that are really far away. And the way we do that is we point the telescope in that location and we keep it there. And we open the shutter on the camera and we keep it open for a long time. Just like your phone or your SLR camera, when it's in dark conditions, it will take a slightly longer exposure to see fainter things. We do that too, but instead of an extra fraction of a second, we are actually keeping the shutter open, not for minutes or hours, but weeks at a time. So we keep this thing pointed for a few weeks, and then collect as much data as possible, as much light as possible to see the absolute faintest distant galaxies, close the shutter, download all the data, process it for a few weeks to make sure everything's accurate. And once we do that, we get this final Hubble Ultra Deep Field image. And if we can pull up image number 1, this is it. It is full of stuff. And what I just want to emphasize is this is a very, very small area on the sky. If you took a penny and held it at arm's length, that would be much, much, much bigger than this image. It would actually be like the eye of Abraham Lincoln on the penny. If you held it at arm's length, that's the area, that tiny, tiny pinpoint of area on the sky that is filled with all of this stuff. And it's almost all galaxies, and it's kind of amazing that the universe is so full of this stuff.
Fascinating. So, okay. Ooh, tiny.
Oh, you got your penny. Great.
And so, I mean, that image that you just showed us, if we were to look at that through, our regular eye or a regular telescope, we wouldn't see any of those bright images. It would just be black.
Yeah, that's right.
If we bring up image 3.
Oh, okay.
There you go.
That's
what the digitized sky survey sees.
Ah.
Now bring up image 4, and you can see, there you go. That's what Hubble sees.
When you hold the shutter open long enough, it brings out that light that wasn't visible before.
Absolutely.
Wow.
And get a much bigger telescope and put it in space.
Yeah, exactly. Now, Frank, all of this that we were seeing in that last image, are those all galaxies?
No, most of them are galaxies. But if we bring up image 5, yeah, there you go. Okay, so there are a few stars. There's about 10,000 objects in this image, and about 500 of them were classified as stars. And here are 4 really bright ones where you can see the diffraction spikes. And of course, these are stars that are in our own Milky Way galaxy, right? And if we bring up image 6, you can see that we've got some big galaxies that have the spiral arms or the elliptical shapes that many are familiar with. Image 7, shows you some of these more distorted galaxies and irregular galaxies. And image 8 shows you that we have some galaxies that are really teeny and they're probably extremely distant and far away. So we have just a smattering of stars, but we've got galaxies out to about 12, maybe 13 billion light years away from us here.
Wow. And the colors that you just showed us on those very, very distant galaxies, are those assigned digitally, or is that the actual?
Those are the colors that come from the processing of the Hubble data. Now, the filters are assigned different colors, so that the longest wavelength filter is assigned red, the shortest wavelength filter is assigned blue, but it's not exactly what the human eye would see because this is a scientific instrument, okay? And the filters are designed to pull out the science that we need. So it doesn't really match what you would get if you had an iPhone the size of Hubble,
The iPhone 28. That's now, Brian. How does a picture like this let us look back in time?
Yeah, so key to understanding that is to know that light travels at a finite speed. It's not infinite. It's very, very fast, but it's not infinitely fast. And so it still takes time to travel between celestial objects that are really far apart. And so, the sun, the light from the sun that we see takes 8 minutes to get to us. And when we look at the sun, don't look at the sun. But if we were to look at the sun, we would be seeing it as it existed 8 minutes in the past. And it's the same thing with these galaxies, except they are much, much further away. The typical galaxy in this image is the light has been traveling to us for 8 billion years or 10 billion years until that light happened to hit the mirror of our telescope. And some of these galaxies, it's been traveling over 12 billion years. And so we are seeing those galaxies as they existed long in the past, in the infancy of the universe, when these galaxies were first starting to form. Fascinating.
12 billion light years. That's a lot of 8 minutes.
Right. And the universe is 14 billion years old. And so, the universe was really quite young. The universe did not start with galaxies and stars. So we're really looking back at the beginning, at the formation of the creation of these galaxies.
That's fascinating. Now, Frank, you've done work with this image, right?
Yep. And we have we've taken all the scientific measurements and turned them into a 3D model. So if we could bring up that first video. It starts with a 2D Hubble image, and then we take the measured distances to all these galaxies, and we stretch them out to form a 3D model. So this is a model of the Hubble Ultra Deep Field in 3D, showing those galaxies stretching across more than 12 billion light years of space. So you get to actually see it all stretched out like that.
Wow. That, because you were talking before about how the different colors show the different distances. That's the data you're using to determine where those go on the 3-dimensional model.
Exactly. I mean, we after doing the Hubble Ultra Deep Field, we got some distances from that, but we also had a lot of ground-based follow-up to measure other distances.
Oh.
And then,
okay,
let me go. And then once you've got that 3D model, what do you want to do with it? You want to fly into it. Okay, let's bring up the second video. All right, so this is a 3D fly-through of the Hubble Ultra Deep Field. And I've choreographed a little camera swoop and such to fly past some interesting galaxies. You can see the various shapes of the galaxies as we fly out into the universe. But here is where that space-time, our time warp view of the universe comes in, because the further we go into it, the further back in time we're seeing these galaxies. Right. Yes. The farther out in space you go, the further back in time you're seeing. So these galaxies are about 10 billion. We're seeing them as they were 10 billion years ago. And we're going to finish with a tiny, what I like to call a red dot galaxy. This is one of the oldest galaxies we've ever seen, or the most distant galaxies we've ever seen. And it's seen as it was more than 12 billion years ago. So this is a galaxy that's just beginning to develop, and only the core of it has had time to form.
Oh,
That's kind of cool, isn't it?
that's incredibly cool. That's amazing. Now, it's noticed that some of the galaxies look different in different parts of the video. Brian, why is that?
Yeah, it's basically because as Frank was saying, we're looking back in time, and so the further away a galaxy is, the further back in time we're looking, and we're looking over a span of time, 12 billion years, where these galaxies have basically formed over that period of time, from being baby galaxies to full-fledged spiral galaxies today. And so we are watching that evolution. Now, we could pull up image number 2. Yeah, these are snapshots of different galaxies at further and further different distances as we go from left to right. And these are galaxies that might be similar to one another, but they're snapshots at different times because we're looking further and further back. And we're looking so far back that the one on the right is just a baby galaxy. And it may not be surprising then that it's a single small little clump of stars as it starts out. But that small little clump of stars pulls in more and more gravity. With gravity, pulls in more and more gas, and that gas condenses and creates more stars. So you see in the next image, these big clumps, bright clumps that are forming a lot of stars. And eventually, after it pulls in a lot of gas, creates a lot of stars, it runs out of most of the gas and it quiets down a little bit. And that allows for some more subtle structure to form, like this spiral at the very end on the left. So this is an approximation of the kind of sequence of evolution that these types of galaxies go through over those 12 billion years.
So this is basically the star equivalent, or the galaxy equivalent of that image of the monkey to the man.
That's right. And you can't watch it happen because it takes too long.
Right. That's incredible. Now, if anybody out there is watching and you've missed the beginning of the show, then you missed our great title card that said Ask the Astronomers Live, because that's what the show is. And if you're watching us live on Facebook or YouTube, go ahead and put your questions in the comments section there on the stream. And again, for new folks, today's topic is how the Hubble Ultra Deep Field, a single image from the sky, can show us the history of our universe and the evolution of galaxies over time. All right, let's see, guys. Let's see if we have a couple of questions here. Yes, here's some questions from our audience. Oh, good. This is one I was going to ask myself. What got you interested in studying the early universe? Frank, you want to start?
Well, actually, this was the topic I studied for my PhD thesis. I did computer simulations of how galaxies formed in the universe. And what we did was, we sort of made a guess at what the early universe was like in a computer simulation and watched galaxies form. And the opportunity to do that when I was at when I was in graduate school just fascinated me because you could really trace the whole history of the universe. I mean, when you learn in history class, you go back a few thousand years and such, and there's tons and tons of stuff. But the idea of extending that back to billions of years back in time, that's just a fascinating thing. It's a really cool problem to solve. That's what got me in. I love solving problems.
Sort of the archaeology of astronomy. Brian, what about you?
So what got me interested? It's a very simple answer. It's Hubble. So I grew up like a lot of kids wanting to be an astronaut. So I just was generally interested in space, and I went off to college wondering, whether I was going to be an engineer, like an aerospace engineer doing stuff with space, or be an astronomer actually studying space. And while I was there as a sophomore or junior, Hubble had launched a few years before into space, and they put a new camera on it, and they came up with the predecessor to the image we're talking about now, called the Hubble Deep Field. And I remember looking at that when I was an undergraduate, and that is what I think convinced me to ultimately pursue astronomy and get a PhD. So it was Hubble.
Interesting. And how much time was there between the Hubble Deep Field and the Ultra Deep Field?
About 9 years, 8 years.
It was 7 or 8 years, because
okay.
the Deep Field was 1995 or 96, and then the Ultra Deep Field was 2003, 2004. We had to call it Ultra, by the way, because we put up a new camera that could do better. All right, and so you've already got this amazing deep field, so it's ultra deep now.
Well, that works better than Deep Field Max. Yeah.
Don't ask what we're going to do with the next one. Deep Field Max, maybe that's what we'll do.
There we go.
Yeah, is there a way to? Oh, wait, we have a question here from Moth of War. Ooh, this is a great question. Are black holes found in the early universe?
I can take it.
Cheers.
Okay, yeah. I mean, my PhD was actually on black holes in the early universe. So, yes, we find them all over the place, and we find them out to the same distances that we find these star-forming galaxies. There are likely massive black holes, millions or sometimes billions of times the mass of the sun in the centers of these galaxies, and they exist out to the earliest galaxies. When we look 13 billion years in the past, and the only way we can see them is because they're black holes. They don't, by definition, they don't emit light. But before the stuff falls into them, it swirls and heats up and gets really, really bright before it falls into the black hole. And that light can actually be brighter than the entire galaxy that it's in. And then we can see that light. So yeah, they're out there, and we see many of them.
See, that's fascinating, because when Moth of War asked that question about black holes in the early universe, I was thinking, oh, because aren't black holes like dying stars? And you were just showing us, a galaxy on its, birth, the birth of a galaxy. How do those things? But then again, I guess, Brian, it's because we're looking so far back and covering so much time. We're seeing birth, death, and everything in between.
Well, Phil,
I mean, you're bringing up. Oh, Frank, please.
I was just going to say, Phil, you have to recognize that a black hole can form in 50 million years. Most massive stars that form these black holes only live for like 10 to 50 million years. So about a billion years is not, you can form a lot of black holes.
Yeah.
But it is sort of a mystery how big some of these early black holes that we've been finding, how they get so big so fast. So you're exactly right. This is one of the big mysteries that we're actively trying to solve, is how in the world did these black holes get so big so fast? So we don't actually know the answer to that yet.
Wow. Fascinating. Let's see if do we have another question? Yeah, Frank, you can take this one. Can you tell us a bit about your experience in combining your astronomy expertise to your visualization expertise? Yes.
Right, so,
basically, this is, what's your origin story, Frank? How did you become an astrophysicist?
Well, it was kind of by accident, okay? I was doing my postdoc at Princeton University, and I was doing the computer simulations of forming galaxies, and we were approached by an IMAX film director who wanted to show the formation of galaxies. He wanted to show the time evolution of the universe. And he said, can you tell our artists what to draw? And we said, no, we can't. We can show you our simulations, but we can't tell you exactly what to draw. And they saw the simulations and they said, all right, this is cool. Why don't we try and use these simulations in the IMAX film? So I ran my PhD simulations on a supercomputer in Illinois. We visualized them with the help of the group at Illinois. And so my PhD thesis simulations appear in an Academy Award nominated IMAX film. Yeah, that's quite the start. And so it's been, downhill from there, I guess. But I've been doing visualizations ever since.
Right. I mean, that's such a great start. That could be the end. I'm out. That's great. Oh, my goodness. Here we go. Oh, now this is a good question. Could one of these galaxies that we see in the ultra deep field have grown up, so to speak, to become like our Milky Way? This takes us back to the development, the evolution of galaxies. What do you think, Brian?
Yeah, so if we can pull up that image 2 again, that shows the sequence of galaxies. There we go. Yeah, so a lot of these are quite big galaxies. The Milky Way today is a quite big galaxy, and so these are likely very similar to predecessors of the Milky Way. Of course, none of them is the predecessor to the Milky Way, but we think that they will have a similar sort of formation history, and ultimately will have formed, we can't see it yet, but have formed into something like the Milky Way today. Having said that, most of the galaxies in the universe generally are much smaller than the Milky Way. And most of the galaxies in this image are much smaller, are really, really small. And so most of them will not form into something like the Milky Way. Only the kind of biggest ones at each epoch, at each interval in time.
Oh, okay. And basically we'll have to wait 12 billion years to really know for certain whether that
Yeah, and if not, we'll publish a correction if we're wrong. So, I promise.
Wait, we have another audience submitted question here. Let's see. This is from Jesse Shires, I think. How does the Hubble manage to stay pointed at the same tiny spot for 11 days without wiggling? And because actually this was a question I was going to ask. And do you have to worry that something is going to come in front of the dark spot, in the weeks that you've when you're doing a Hubble deep field? But answer Jesse's question first. How does the Hubble manage to stay pointed in the same tiny spot? Who wants to take that?
I'll take it because all right. So Hubble has guide star tracking. Okay, so it has 3 cameras on it that are specifically designed to follow specific guide stars. So when you plan an observation, you also have to plan what guide stars. And so the roll and pitch angle of Hubble is always adjusted to keep those guide stars, that set of guide stars, in their individual pixels. All right. They're not looking through the camera that you're taking the observation with. You're using the guide stars to do this. And the second thing is that while we do have 11 days of exposure, it's taken in about 45-minute increments. Because Hubble is orbiting around Earth, and if it's behind Earth, and you can't see the spot, you can't take it. You can't take an image. You have to close the shutter. So it opens and closes the shutter about every 45 minutes. In order, so the actual image is an accumulation of hundreds of these shorter exposures.
I see. Okay, so it's not just like you said, Brian. It's not just an iPhone taking one shot. It's a much more complicated, computerized process. But that's interesting to know about the guide stars. That's how Hubble keeps itself focused on the same spot. Got it. Okay. Let's see. Do we have any more? Yes, we have one more question. Has there been any particular reactions that stand out to you from non-astronomers viewing the video?
Yeah, there have been quite a number of interesting ones. There was one that said, "That just melted my face."
What?
And basically a lot of people going, oh, I feel so small now, seeing how big the universe is and all of the things. And one of them was like, oh, I almost started crying. And then I absolutely love the sarcastic response to that. I started crying so much I had to be sent to the hospital and sedated. So yeah, people have been very moved. People are very moved by cosmology and the expanse of the universe, and the great lengths of time and the great number of galaxies and stars there are out there.
Wow. Okay, so you've inspired people to take the depths of the galaxy very, very personally. Now, before we wrap up, are there any final thoughts that you guys would like to share with the audience? Anything that we didn't get to go into enough, or just stuff that you're working on that you'd like us to know about? Brian, why don't you start?
Well, I guess I'm going to add to what was just said here, that people they love the image of the Hubble Deep Field, and I've shown it publicly many times. But I think what actually adds to it is the scientific knowledge. It's a beautiful image, and people are inspired by it. But actually, when they know the details, that it's this tiny, tiny, pinpoint through the sky, that's actually when it, they get dizzy thinking about it, and it's kind of awe-inspiring. And I just really like the fact that bringing in scientific knowledge to what is also art is what really is inspiring. And so sometimes science and facts and details like this can be quite inspiring by themselves.
Yes, absolutely. I mean, yeah, you guys are inspiring on an artistic level, but with facts, because it affects us in that same way. It takes us back through our lives, back through our history, not just of us on this planet, but as far back as we could possibly imagine. And that triggers so much in people, emotions, ideas. That's wonderful. Frank,
Yeah.
any final thoughts for us?
Well, I would probably just riff off of what he just said, in terms of that I have a really cool job because I get to combine science and art. And I do talks for high school students. And, the science geeks are all excited about, oh, there's an astrophysicist coming. And the art students are like, oh, boy, you got to listen to another STEM talk. But the point is at the end of it, hopefully I've convinced some of the art students that they can apply their art to STEM fields, and some of the STEM students that they don't have to be just this geek, they can actually do art. Because we create these movies. I mean, I'm an astronomer who makes movies. How fun is that? And it is exactly what Brian said. It's the knowledge of the truth behind the beauty that gives it its ultimate power.
Exactly. Truth and beauty. Before we go, we have one more question. This one is specifically for you, Frank, from Ann McCarthy on YouTube. Right. How did you get into museum work?
Well, I was a postdoc at Princeton, as I said, and the office next to me was occupied by Neil deGrasse Tyson. And Neil and I got to be friends, and we chatted, and I showed him some of the visualizations I worked on for the IMAX film Cosmic Voyage. And then he was offered the head of the Hayden Planetarium in New York City. And he still came down to Princeton a little bit. And when my postdoc was up at Princeton, he offered me a position as working on the rebuilding of the Hayden Planetarium in New York. So for 5 years, I was working on the brand new Rose Center for Earth and Space. It was Neil Tyson, Steve Soder, and I were the three curators that built that brand new museum that opened in 2000. So I guess it was luck of office space and being by somebody who eventually ended up in museum work and dragged me into it.
There you go. Good luck. And also be nice to your office mates.
There you go.
Wow. Thank you both so much. And thank you guys out there for joining us today for our journey through billions of years of cosmic history as seen in the Hubble Ultra Deep Field. Now, you can see the whole 3D movie that was made from this image, as well as all of our other videos at universeunplugged.org. Or you can just click on the link in the comment section there for those of you on YouTube and Facebook. And make sure to subscribe to Universe Unplugged on YouTube, follow us on Facebook, so that you don't miss any of these great shows and these fantastic guests. Thank you, Dr. Frank Summers. Thank you, Dr. Brian Sayana, for sharing your knowledge and your creativity, guys. Thank you very, very much. Till next time, I'm Phil Lamar, and this has been Ask the Astronomers Live.